let's start playing around with what the standard deviation can actually do for us. I need to change my pen color here real quick. So we know the standard deviation is the average distance, more or less. Remember, there's that little n-1 thing that can drive us a little crazy. More or less, it's the average distance of the data values from the mean. That's a great way of thinking about it. So big standard deviations means that the data values are all over the place, both sides of the mean. Small standard deviations means everything's packed, grouped very tightly around the mean. But there are much greater ramifications of the standard deviation. For example, watch this. I made a pretty bold claim here that this 7 value, the kid that had 7 siblings, was an outlier. Well, there's actually a rule of thumb that I'm going to show you. It's called the rule of thumb for outliers, for usual values. For usual. Now, usual is kind of strange, but watch what happens. The rule of thumb is this. Excuse me. The minimum value in a usual set should be greater than or equal to the mean minus 2 times, let's go big dot, times the standard deviation. And this is a minimum usual value. The maximum usual value should be less than or equal to the mean plus 2 times the standard deviation. All right? Now, let's look at number 7. Change colors real quick. Let's look at this value right here. We're going to check to see if this is an unusual value. All right? Well, it's clearly bigger than the rest, so I don't really have to check to see if it's a minimum. If I take 1.8 and I go plus 2 times I'm going to just cheat a little bit here and say that this is 1.7. I'm using this standard deviation because I'm using this formula down here. 2 times 1.7. Then the max, we know that the max normal value should be less than or equal to 1.8 plus 2 times 1.7, which is 1.8 plus 3.4, which is what? 5.2. Hey, my spidey sense is tingling. My bunny ears are up. This is a big freaking number. So I got to pay attention to it as an outlier. It's going to do strange things to everything. Think about what would happen. If I removed this 7, what would happen? Well, would it change my mean? Most certainly. Instead of being close to 2, it'd be closer to 1. Would it change my standard deviation over here? Absolutely. Think about that. All of these numbers would be grouped between 0 and 3. There's no way that the average distance of the data values would be 1.699. It'd be a lot tighter, be a lot smaller. Okay? So now we have this cool little rule of thumb for unusual values. Now, on that same vein, I'm gonna shift gears into something that I know that we've all seen. Let me change colors real quick. Whoops. Something that I know that we've all seen. Now, the book refers to this as a bell-shaped curve, but I'm going to get way more specific. This is the rule of thumb, thumb for normal. Now, we've heard of normally distributed variables, maybe. Normal or bell-shaped curves. Sorry about my handwriting, you guys. Okay? Now, let's do this. Any bell-shaped curve or any normal curve, regardless of the mean and the standard deviation, we have what's called a 68, 95, 99.7 rule. This is the rule of thumb for bell-shaped curves. You know what? I need a bigger curve. So, pardon me, I'm going to erase this and make it something I can work with. All right? Now, here we go. Let's see, where am I? I'm going to make a fat daddy. Ugh. Looks like an anaconda that ate a goat. All right, so we know, hopefully from the symmetry argument that we made before, we know that the mean is going to live in the center. Now, if you know calculus, and I'm not expecting that you do, but if you do, there's actually a way to figure out what one standard deviation is, excuse me, on this curve. It's actually the place where the curve, pardon me, changes concavity. So it's this distance. I know that the distance from here to here is 1 standard deviation. It's also this distance. You know, there's a better way. That looks like a 5. This is sorry you guys, this right here is 1 standard deviation. Right here. So we're going to go, whoop, this is the standard deviation. Remember, standard deviation is a distance, so I'm gonna write it the same way. Now, let's change colors real quick. I know that as a rule of thumb, and we'll prove this numerically down the road, if I go 1 standard deviation away from the mean on either side, I know that 68%, approximately 68% of all the data is going to live 1 standard deviation away from the mean on either side of the data. If I go another standard deviation, which would get me out to what about there? So think about this. Now this distance right here, my pen's going crazy. Now this distance right here, go away. This distance right here is 2 standard deviations. This distance right here is 2 standard deviations. If I go 2 standard deviations away from the mean on either side, I end up with 95% of the data. 95% of all data values will reside within 2 standard deviations from the mean on either side. Now, let's change one last time. If I go out 3 standard deviations, I don't know how I'm going to do this, but what the heck. I'll just do it with color. How's that sound? I know that 99.7% of all of the data resides within 3 standard deviations away from the mean. That's a monster rule that we can use when we have a normal or a bell-shaped curve. Look, statistics, because it's so complicated computationally to do stuff sometimes, it can rely really heavily on these little rules of thumb, these little mnemonic devices that we can use to help remember things. Okay? Now, let me give you a little bit of vocab, and then we'll have a little more fun with standard deviations here in just a sec. All right? I'll give you a crazy term called Chebyshev's theorem. All right. There's something called variance. All right? Which should be easy to remember because it comes from variation. And it's actually really simple to define. It's simply the square of the standard deviation. That's all it is. So if I'm talking about sample variance, now think about that. If S is the standard deviation, remember, sample standard deviation because it's just lowercase letter, then S squared is sample variance. All right? If sigma is the population standard deviation, then sigma squared is the population variance. Okay? Nothing to it. Now you may say, wait a second, Ripley, didn't we just do a whole computational deal that made it so that my units remained consistent? Remember back when we computed, if I stumble back here, remember I waved my hands and screamed and yelled and said, wait, we end up with kids squared and we want standard deviations to be in terms of kids. You're absolutely correct. However, that said, there are statistical procedures that actually use standard deviation, or excuse me, that actually use variances. Okay, so it's good to know how to figure those things out. All right? Okay, now, we got these cool rules of thumb. We got the one that says a usual value is within 2 standard deviations from the mean, regardless of the shape of the distribution. If we know that the shape of the distribution is normal or bell-shaped, I have this 68, 95, 99.7 rule. We will put this into practice, by the way, in class. So I'm not just throwing it out there and assuming that you're going to know it and let's move on. We're gonna have some fun with it down the road. Excuse me. However, there's something that's really cool. It's called Chebyshev's. Let's get the pen working. Chebyshev's theorem. Guy's clearly Irish, right? Nah, just kidding. Got to be Russian. Okay? And Chebyshev's theorem says this. It's actually a real simple formula. It says if I let K equal the number of standard deviations from the mean of any, now this is really important, any distribution All right? It doesn't have to be bell-shaped. It doesn't have to be uniform or look like a rectangle or anything like that. It can look like anything. It can be one of those bimodal ones. It can be as crazy as it wants to be. Okay? If I let k equal the number of standard deviations away from the mean of any distribution where k is greater than 1. Now, remember in math speak, this implies that 1 minus 1 over k squared is equal to the proportion, proportion, which is actually the minimum. I'm going to stick the minimum. So let's write it like this. The minimum proportion of data values that lie, or lay, I always screw that up, in that range. Now I'm going to show you what I mean here, because this one's going to require me to hem and haw a little bit. Think minimum proportion. Well, let's play for just a sec. Regardless of the distribution, let's say that I let k equal 2 standard deviations. All right? Now, remember, the distribution could look crazy. Let's go back. Let's go over here. I'm going to grab a new page because that one's starting to get a little crowded. All right, so remember, Chebyshev's is 1 minus 1 over k squared. And I'm going to let k equal 2 standard deviations. Now, let's say that we have a distribution that looks like this, something crazy, okay? Let's say it goes like that, okay? Clearly not bell-shaped. It's got this crazy right skew to it. Remember, the mean's going to be sucked over towards what appear to be outliers. The median's going to be somewhere between the mean and the mode is going to be at the high point, right? I don't have a rule of thumb for this kind of distribution. But I want to know, let's say that my mean, just for giggles, let's say my mean lives right here, all right? And we're going to assume that this is a sample. I know that 1 over 1 minus 2 squared, which is affectionately known as 3/4, which is equal to 0.75, sorry you guys if I'm boring you, or 75% of all data lives within 2 standard deviations. Now think of it this way. This is really an at least. It's the bare minimum. So at least 75% of all data lives within 2 standard deviations. Well, we know that that's not a strange thing to say. Remember over here when we had a bell-shaped distribution or a normal distribution, we know that 95% of all the data live 2 standard deviations away, but that was only for a normal distribution. Let's say that we go, I don't know, let's let k equal 1.5, or affectionately known as 3/2. Well, according to Chebyshev's, 1 minus 1 over 3/2 squared, which is 1 minus 4/9, which is 5/9, which is equal to 0.55 or 55.5%. That's like that, right? All right, so at least, this implies at least 55.5% of all data lives within 1.5 standard deviations. Now, I'm going to write something up that's really important. I'll bring it. It's so important, I'm going to bring it up here. Regardless of the shape of the distribution. Muy importante. It's huge. That's why Chebyshev's makes it in. I mean, look at this thing. It's like the simplest thing you've ever seen in your life. I actually had to prove this in a statistics class that I took. And I'll tell you what, for such an easy formula, proving it was no joy. It was, I'd rather, I don't know, saw my foot off with a spoon. I think I've said that before. I don't know what's going on with spoons in my feet. All right? All right. I think we're just about done with all the fun that we can do with standard deviations for the time being. I gave you some vocab. You got variance, Variance is easy to remember because of variation. Variance is just the standard deviation squared. So if I give you the standard deviation, I can always get to the variances. Just remember, if it's lowercase, regular old alphabet, alphanumerics, then you're talking about samples. If it's lowercase Greek, you're talking about populations. Hope you enjoyed, and we'll see you in the next.